Solve problem 7.1 Curling. The red curling stone of 19 kg has an initial velocity of 1.60 meter per second in the x direction and is deflected after colliding with an identical yellow stone which is at rest to an angle of 32° relative to the x-axis. What are the two final momentum vectors right after this collision? And what is the sum of the stone's kinetic energies? So here in this question, you have a red curling stone that has a mass of 19 kilogram and it is moving with an initial speed which we write as V initial 1 of 1.6 meter per second along the x-axis, and it hits another yellow identical curling stone which is initially at rest. So we write V initial 2 to be 0. After collision, the red stone is deflected by an angle theta 1 of 32°. So we write theta 1 as 32 with respect to the x-axis. We need to find what are the two final momentum vector right after the collision. So to solve this problem, we are going to use the law of conservation of momentum. But before we use the law, let us first find out what are the components of momentum vectors after collision. The red stone is deflected at an angle of theta 1 from the x-axis. So we can split this into two components. One that goes along the x-axis, which we call as P1 final x, and one that goes along the y-axis, which will be P1 final y. The second stone, which is the yellow stone, it is deflected by an angle of theta 2. And since this is an example of elastic collision, we know that in elastic collision, when two objects collide, they move at an angle of 90 degrees with each other. So we get theta 1 plus theta 2 to be equal to 90. Or we can find theta 2 from this as theta 2 equals 90 minus theta 1, which is 90 minus 32. That gives you theta 2 as 58 degrees. Then we split the components of the yellow stone. One component that goes along the x-axis, which we write as P2 final x, and the other that goes along y-axis, which will be P2 final y. After we split the components, now we can use the law of conservation of momentum. Law of conservation of momentum says that momentum before collision has to be equal to momentum after collision. And since this is an example of two-dimensional motion, I have to apply this law to x-axis and y-axis separately. So let us start with momentum along y-axis. So initial momentum along y must be equal to final momentum along y. Initial momentum along y-axis is 0, as the red stone is only moving along the x direction, whereas the yellow stone is initially at rest. So since there is no velocity along y-axis, momentum along y-axis will be 0. Final momentum along y-axis will be sum of momentum of the red stone and yellow stone along y-axis. So we write P final 1 y plus P final 2 y. So we get 0 equals, for the red stone, the y component we can write as P final 1 sine theta 1. Whereas for the yellow stone, the y component is going down, so we will take it negative. So minus P final 2 sine theta 2. Rearrange them, move this to the other side. We get P final 2 sine theta 2 equals P final 1 sine theta 1. Divide by sine theta 2, we get P final 2 equals P final 1 sine theta 1 over sine theta 2. We will call this as equation 1. Now we do the same thing for momentum along x-axis. We write P initial x to be equal to P final x. Along x-axis, the initial momentum is because of the red stone as it is moving in the x direction. So we write its momentum as mass times the initial velocity of the red stone equals Final momentum is because of the red and the yellow stone, and we can write their final component as P final 1x plus P final 2x. So we get MV1 initial equals P final 1x is the x component of the red stone after collision, which we can write as P final 1 cosine theta 1. We do the same thing for the yellow stone, P final 2 cosine theta 2. Both x component are going to the right, so we keep their respective values as positives. Now substitute for P final 2 from equation 1 here. We write MV initial 1x equals P final 1 cosine theta 1 plus, in place of P final 2, I'm going to write P final 1 sine theta 1 over sine theta 2 into cosine theta 2. Now take P final 1 common on both sides. So we get MV initial 1x equals P final 1 cosine theta 1 plus, write this whole thing, sine theta 1 times cosine theta 2 over sine theta 2. I want to find what is P final 1, so divide by this whole thing. So we get P final 1 to be equal to MV1 initial x over cosine theta 1 plus sine theta 1 into cosine theta 2 over sine theta 2. Now let's substitute. We get P final 1 to be equal to mass of the curling stone is 19. Initial speed of the red stone is 1.60 over cosine theta 1 is cosine 32 plus sine theta 1 is sine 32 into cosine 58 over sine 58. And when you solve this, you get the final momentum of the red curling stone to be equal to 25.78 kg meter per second. After we find P final 1, we will substitute this in equation 1 to find P final 2. So we have here P final 2 equals P final 1 sine theta 1 over sine theta 2 into cosine theta 2. Now let's substitute the values here. We get P final 2 equals P final 1 is 25.78 sine of theta 1, which is 32, cosine theta 2, that is 58 over sine 58. And when you solve this, you get P final 2 to be equal to 16.1 meter per second. Then the next part of the question wants us to find what is the sum of the stone's kinetic energies. So we can write sum of the kinetic energy as K equals kinetic energy of the red stone plus kinetic energy of the yellow stone after collision, which we can write as P final 1 squared over 2m plus P final 2 squared over 2m, because kinetic energy in terms of momentum is P squared over 2m. Since the mass of the two stone is equal, we can write this as 1 over 2m P final 1 squared plus P final 2 squared. Now substitute. K equals 1 over 2 times 19. P final 1 is 25.78 squared. P final 2 is 16.1 squared. And when you solve this, you get their total kinetic energy to be equal to 24.3 joule. So anytime you have a problem in 2 dimension, you will use the law of conservation of momentum the same way we do for 1 dimension, but treat the x-axis and y-axis separately. And then you can find the resultant by either using Pythagorean theorem or what we did in this particular problem. Kinetic energy, on the other hand, is a scalar quantity. So once you found the final momentum of the red and yellow stone, you can just add the kinetic energy values of the individual stones.